Hey, welcome to yet another session for the Flipped Classroom for AP Calculus. This is section 34, Substitution in Definite Integrals. That would be section 4.6 in your book. U substitution. Remember, we've learned how to do U substitution for indefinite integrals, and now we're just going to use it for definite integrals where you know the limits of integration. Here's an example problem, okay? So let's say we have the integral from 1 to negative 1 of 3x squared times the square root of x cubed plus 1. Okay, the first job is we have to find out what u is. Well, you can see that if I let u be x cubed plus 1, then it's very nice that du dx turns out to be 3x squared, which I already have in the integrand, okay? So then du would be equal to 3x squared dx, so it's a direct substitution. So our second step would be to rewrite our integral in terms of u. This would be the integral of the square root of u du. Next step is find the antiderivative of u, and f of u, you have to be careful how you say that, is 2/3 u to the 3/2. Then what we're going to do is we're going to back substitute in for u. So f of x, the antiderivative of x, is 2/3 quantity x cubed plus 1 to the 3/2. Evaluate antiderivative of 1 minus the antiderivative of negative 1, and after you do all the math, you get that the integral is 4/3 square root of 2. Now, notice that we wrote u as an indefinite integral. There is another way to do this where you change the limits of the integration to in terms of u, and I'll show you that on the next slide. Okay, if you would like in the previous problem, you can rewrite the limits in terms of u. So if u equals x cubed plus 1, then our a, which is negative 1, would be negative 1 cubed plus 1, or 0. And b, which was, I believe was 1, would be 1 cubed plus 1, which is 2. Then you can just directly evaluate the antiderivative of u, 2/3 u to the 3/2, at antiderivative of 2, f of b, minus f of a, f of 0 really, and you see you get the same answer. Okay, sometimes it's easier to do it one way, sometimes it's easier to do it the other way. Okay? Here's another sample problem. Let's find the integral of the cotangent of theta times the cosecant squared of theta from pi over 2 to pi over 4. Okay, so you have to ask yourself, what should I let u be? And what I do is I say, okay, if I have u, I know I'm going to have du, and I want to look to see if du is present in the integrand. So there's a couple choices. I could let u be cotangent of theta, and then du would be negative cosecant squared of theta. That would work. Or I could also yet let u be cosecant of theta, and du would be negative cosecant cotangent of theta, d theta. Either way, this works, okay? The only thing I need to do is I need to have a negative sign. And I can create a negative sign very simply by just bringing a negative sign to the outside and leaving a negative sign on the inside of the integrand. So I rewrite the integral as the negative integral of u du. Integrate it, I get the negative u squared over 2. Back substitute what u was, I get negative cosecant squared of theta over 2. Evaluated at pi over 2 and pi over 4. That would be f of b minus f of a. Here's the math, back substituting, actually substituting b in here, a in here, and it all comes out in the wash as 1 over 2, or 1/2. Alright, let's talk about how to find the area between two curves, okay? Well, there's a theorem that says if f of x and g of x are continuous from a to b, and f of x is greater than g of x on the closed interval ab, then the area between f of x and g of x is the integral of f of x minus g of x. This implies that f of x is on top of or greater than g of x. And we would evaluate this at b and a. So our steps for finding the area between two curves. 1. Graph the functions in order to see which function is greater or on top. Find the limits of integration. 3. Write an integral for f of x minus g of x. 4. Integrate f of x minus g of x from a to b. That's it. Here's a sample problem. Let's find the area of the region bounded by two curves. First of all, we have y equals 2 minus x squared. That would be this red parabola. And then y equals negative x, the green line. Okay. Step 1 I've already done here is graph it. Next, determine which function is on top. Okay. Obviously, 2 minus square root of x. 2 minus x squared is on top. Okay, how do you find the limits of integration? Well, if you look at this curve, it says I want the area of the region bounded by these two curves. Okay, that would be this region here. So how do I find the limits? Well, it looks like this would be a limit right here, and that's a point of intersection, and this would be a limit. Okay, so what I do is two curves intersect when they are set equal to one another. We set them equal to each other, and we find out that they intersect at x equals negative 1 and x equals 2. So negative 1 will be my a, and 2 will be my b. Integrate the top function minus the bottom function, because what I really want is imagine that there's a rectangle here. I need to know what would that height of rectangle be at a certain value of x. Well, it would be the total value of the top function minus the value of the bottom function. So I set my integral up as the integral of 2 minus x squared minus, okay, subtracting the next one, minus x, okay, from negative 1 to 2. Find the antiderivative of that. It turns out to be 2x minus x cubed over 3 plus x squared over 2. And then just find f of b minus f of a. When all is said and done, it turns out to be 9/2. That means that the area between these two curves from negative 1 to 2 is 9/2. Sometimes you have to change your integral throughout the interval that you're doing to match a boundary change, okay? Let's look at this problem. Find the area of the region in the first quadrant that is bounded above by y equals the square root of x, okay? This red curve is y equals the square root of x. And below by the x-axis right here, and the line, this green line, is y equals x minus 2. Notice, I've drawn in two rectangles here, okay? For this area here, up to from 0 to 2, really the only thing I care about as being the height of this rectangle is the function value for the square root of x. But when I get from 2 to 4, the size of the rectangle in my area that I need is really going to be this red curve minus what's under the green curve. So this will be the square root of x minus the quantity x minus 2, and that will be from 2 to 4. So I really have two separate integrals. Okay, so the step is to partition the interval according to where the formula for rectangle height changes. Okay, set up integrals for new partitions. So my first integral is going to be y equals the square root of x, okay, from 0 to 2, okay, and then my next integral will be the square root of x, this red curve, minus the green curve, x minus 2, from 2 to 4. If I integrate both of these, okay, and add them together, that will be the total area. So we do the integral, we get 2/3 x to the 3/2, evaluated from 0 to 2, plus 2/3 x to the 3/2 minus x squared over 2 plus 2x, evaluated from 2 to 4. We do the math here, and what comes out in the wash is 10/3. And that would be the area between the x-axis this green curve, the straight line, and y equals the square root of x. So this area right here, that's what it would be. What now? I would like you to work on pages 393 to 394, 1 through 42. Yes, I realize this is the largest assignment, but they go pretty quickly, and you've done problems similar to these in the previous section. Little calculus humor. Here's a reason for not doing your homework. I could only get arbitrarily close to my textbook. I couldn't actually reach it. Get it? See you next time.